You would think the future starts with some big eureka moment, right? A flash of genius. But sometimes it starts with a problem that just has to be solved, like right now. We're going to dive into a master's thesis from 1945 that, honestly, at first glance looks like some dusty old document. But as you're about to see, this thing is actually the secret origin story for the technology that powers our entire automated world. Okay, so picture this. It's 1940. The Battle of the Atlantic is in full swing. Allied merchant ships, which are the absolute lifeline to Great Britain, are getting hammered. And the main reason, as this document points out, was the Nazi dive bomber. It was fast, it was unpredictable, and it was devastatingly effective. A human gunner? They just couldn't react fast enough. No way. So this was the million-dollar question facing Allied engineers. This wasn't just about building a bigger gun or a faster gun. It was about building a smarter one. They needed a system that could track an enemy plane, predict where it was going to go, and fire with a kind of superhuman speed and precision. They literally needed to build a machine that could think. All right, so let's start with the problem itself. Let's dig into this World War II menace that demanded a solution that was not only urgent, but incredibly innovative. The challenge was officially tossed to a brand new group at MIT called the Servomechanism's Laboratory. Their mission was crystal clear: figure out a way to create an automatic fire control system. They had to link a computing site to a 37mm gun and give those merchant ships a real fighting chance. So, how do you even begin to build something like that? The answer was in creating what was essentially a mechanical brain for the gun, using the raw power of hydraulics and this really cool concept called feedback. The key piece of the puzzle was a technology called a servomechanism. And what makes a servo so powerful is this core idea of feedback. It doesn't just act, it's constantly measuring its own action, comparing that to the goal, and then correcting itself, all in real time. It's this beautiful closed loop of sensing and responding. Now, today, you'd solve this with a microchip, no question. But back in 1940, electronics were kind of seen as flimsy and unreliable, especially for military gear. So the team put their faith in high-pressure hydraulics. It was proven, it was powerful enough to swing a heavy gun around like it was nothing, and they were inspired by some really successful British systems that were already out there. And this right here, this is the heart of that system. On the left, you've got the Vickers hydraulic pump. Its job was to take the commands and turn them into pressurized oil flow. And on the right, you've got the motor, which used that flow to create the powerful, precise rotation needed to aim the gun. This was the muscle of the operation. But having the idea is one thing. Actually building it was a whole other story. It was a massive challenge to get from the math on a page to actual working metal, to bridge that huge gap between theory and reality. Before they could turn a single gear, the entire system had to exist on paper. And just look at this page from the thesis. This is the incredibly complex math they were dealing with. These differential equations were their best shot at modeling and predicting how this whole mess of pumps, valves, and motors would actually behave under pressure. But theory, as we all know, is one thing. Reality? Well, reality is usually a lot messier. This is what the first tests actually looked like. These squiggly lines are the raw data from an oscillogram. It's noisy, it's imperfect, and it immediately showed them that the clean, elegant math didn't quite capture the messy truth of the physical world. And right here, the author of the thesis, a young engineer named Forrester, he notes something fascinating. In some ways, the real-world machine actually worked better than their math predicted it would, but in other ways, there were serious problems. The main point is, they now had to figure out why the theory and the reality weren't matching up. This table just lays the problem bare. Look at the numbers. The predicted frequency of oscillation, way off from what they actually measured. But more importantly, look at that bottom line. That's the real villain of our story: steady-state velocity lag. Both the theory and the real-world tests showed that the system had a fatal flaw. Yeah, this flaw, this velocity lag, was the central enemy, and figuring out how to beat it was the project's single biggest breakthrough. So what the heck is velocity lag? It's pretty simple, actually. When the gun was tracking a fast-moving plane, it would always be pointing just a little bit behind it. And for a weapon that needs to hit a target moving at hundreds of miles an hour, slightly behind is the same thing as a complete miss. This lag was, as the thesis says, totally unacceptable. Okay, so on the left, you're looking at the diagram for the first design, the Type I. And on the right, you see the modified Type V that finally solved the problem.
Now, it might look like a really subtle change, just a few extra components tacked onto the bottom, but that little modification was an absolute stroke of genius. The solution was just so elegant. Instead of just commanding the gun where to go, they added a clever new feedback loop. First, it would measure the gun's actual speed. Then it would create a new signal based on that speed. And then, this is the brilliant part, it fed that signal back into the system. In essence, the machine was now aware of its own mistake, and it could learn to anticipate and cancel out its own lag.
So, with the velocity lag problem crushed, the project was a huge success. But its impact, man, it went far, far beyond just this one anti-aircraft gun.
And there it is. From all those pages of equations and diagrams to this rugged assembly of steel, wires, and hydraulic pipes. This is the actual experimental prototype, the physical result of all that brainpower, ready for its final exams. And this graph, this is the proof. This is the report card, and it got an A+. That solid line, curve A, that's the data from the actual working machine. And just look how closely it tracks the dashed line, which was their final corrected mathematical model. Theory and reality were finally in sync. This system flat out worked. And it didn't just work in a nice, clean lab. Nope. They hauled this thing out to Fort Heath, Massachusetts, and bolted it to an actual gun carriage. And under live firing conditions, with all the shock and the recoil of the gun going off, the system performed flawlessly. The report says it produced negligible disturbance. Just incredible. The principles they perfected in this one project started to spread like wildfire. They were adapted for the remote-controlled gun turrets on the famous B-29 Superfortress, for automatically positioning radar antennas, and they really became the foundation for all the industrial automation that exploded after the war. Think robotics, flight simulators, the whole shebang. And that young engineer who documented this whole thing, Forrester, he would go on to become an absolute giant in a completely different field, digital computing. This whole wartime project, solving a very physical, mechanical problem with analog feedback loops, was a crucial stepping stone on his path to creating the very first real-time computers. Which leaves us with a final, pretty cool thought. We live in a world of smart devices, self-driving cars, automated everything. And isn't it just fascinating to consider that the DNA for all of it, it can be traced right back to this moment, to a single desperate problem, and the elegant solution that was designed to shoot down a plane in the North Atlantic.